Okay, hello everyone. And good morning, all of you. And today we will start with the quote. So it says, life is a journey and not a race. Because now people say everything is like a rat race, you have to run. It's not meant only to reach the finishing line, it's meant to make every moment matter and count for a glorious life. That's what I repeated it. You have to enjoy the journey. It's not only the finishing line or destination that makes you happy. So you have to enjoy every moment of your journey. And today is the birthday of great. Anybody knows one of the great person, great Indian
Vivekananda Jayanti.
Vivekananda Jayanti, right? Swami Vivekananda, Indian Hindu monk and philosopher. He says every word of him is inspirational, right? So you go through any book or any speech that is given by Vivekananda with very, very simple words. It's so thrilling and inspiring. Strength is life, weakness is death. Expansion is life, contraction is death. Love is life, and hatred is death. He was a key figure in the introduction of Indian philosophies of Vedanta and yoga to the Western world, and is credited with raising interfaith awareness, bringing Hinduism to the status of a major world religion during the late 19th century. He is perhaps best known of his speech. Everybody knows it, right? So, what is this first sentence? Sisters and brothers of America. So, when he is given few minutes of time, and when he got up and just addressed this, sisters and brothers of America, and people started clapping all the time that is given to him. And later his time is extended. So, in which he introduced Hinduism at the Parliament of World Religions in Chicago in 1893. Vivekananda conducted hundreds of public and private lectures and classes disseminating tenets of Hindu philosophy in the United States, England, and Europe. In India, Vivekananda is regarded as a patriotic saint, and his birthday is celebrated as National Youth Day. Okay, today is National Youth Day. And we talk about one scientist also. So it is Lanier. Have you heard about Lanier? Anybody? If you've gone through the thermodynamic cycles, right? So, but it is not there in the syllabus, but there is one particular cycle, Lanier cycle. Okay, usually every cycle, how many processes are there? Whatever things you have learned.
Four.
Usually 4 processes will be there. Okay, and there is only one process you might have, one cycle with more than 4, I think you learned. What is that cycle?
Dual.
Dual cycle. Okay, and I don't think you have studied any 3 process cycle, and his cycle is 3 process cycle, Lanier cycle. Just you go through Google or Wikipedia, you will come to know about it. And this is one another important thing is the this is constant volume combustion cycle, and this is used in pulse jet engine. This particular cycle is used in pulse jet engine. Okay, pulse jet engine also we will discuss later in the when you talk about jet propulsion. And he invented and devised the world's first commercially successful internal combustion engine. And he moved to Paris, where his work and work with electroplating led him to the other electrical inventions, among them a railway telegraph. Lanier patented his first engine in 1860. Looking much like a double-acting steam engine, you can see that uh, one sketch there. It fired an uncompressed charge of air and illuminating gas with an ignition system of his own design. One of these engines powered a road vehicle in 1863, another ran a boat. Because of improved designs by Otto and Diesel, those people are also competents there at that time. And because of Otto cycle and other inventors, the Lanier engine became obsolete, and only about 500 Lanier engines were built. And unfortunately, this inventor Lanier died poor, right? Because of the competition and of the Otto cycle with this. Okay, this is the great Lanier. And today we'll go for the Navier-Stokes equations. As I told, in fluid mechanics, Navier-Stokes equations are momentum equations, but in CFD, Navier-Stokes equations are the whole governing equation set, right? It's called the Navier-Stokes equations. Okay, just we'll quickly see what we heard on in the last class. Yes, okay. In the last class, we have seen what are all the assumptions made for CFD equations to be valid. Okay, we have discussed various assumptions and the different sciences also we have seen. Okay, then we have seen what is a substantial derivative. So we have defined this as d by dt is equal to dou by dou t plus v dot del. Right, this is called as local derivative. This is convective derivative. And this is substantial or total or material derivative, like this. And then we have seen the physical significance of divergence of velocity, which is equal to, we have proved it to be equal to
volumetric strain rate.
yeah,
Volumetric strain rate.
rate of volumetric strain. And similarly, significance of curl of velocity. What is this?
Vorticity.
Vorticity. And then we have seen different strains, strain rates, like epsilon dot. Actually, dot I didn't put. Usually, rate of because these are rate of strain rates. Normally, dot is put here, equal to dou u by dou x, dou v by dou y, dou w by dou z. Similarly, epsilon dot xy is equal to dou u by dou y plus dou v by dou x. So like that we have. So we have got, which is what is called a strain tensor. Epsilon dot is equal to epsilon dot xx, epsilon dot xy, epsilon dot xz, epsilon dot yx, epsilon dot yy, epsilon dot yz, epsilon dot zx, epsilon dot zy, epsilon dot z. Like that, this is what is called as strain rate of strain tensor. And after that, we have shown that a general movement of a particle involves linear translation, then linear deformation, and angular deformation, and pure rotation. Okay, so this we have shown that if a velocity is v at a particular point, and after at another point, if it is v plus dv, this v plus, it can be written like deformation plus omega cross. Like that. So this is translation. This consists of linear and angular deformations, and this consists of the rotation. And then we try to talk about the continuity equation. We taken 4 types of models, right? So finite control volume. So as I told, these two are finite control volumes, resulting in integral equations. Because we are considering a larger volume, we have to integrate this over the, we get integral equations. And I can have infinitesimal element results in differential equations. And I can consider a fixed control volume through which a flow goes, and this is called as Eulerian system. This results in conservative form of equations. And R, I can have a fixed mass system. This is fixed volume. This is fixed mass. This is called as Lagrangian system.
That should be CV, right? Not FV.
What is that?
Fixed mass system, you wrote again fixed volume. It should be control volume instead of FV.
It's finite volume. This is control volume. This is system. Finite volume. Okay. But it is a system only, closed system. Control volume is different. Control volume, nothing but these are open systems. These two, Eulerian system, open systems, Lagrangian systems, closed systems, which are fixed mass system. Okay. And so we have seen that if you consider this first case, so this is rho by dou t of integral rho dv, the rate of change of mass within the system is equal to minus of the whatever mass leaving the system. So we got this as plus integral rho v dot dA areal integral. This is equal to 0. And this we have proved it. We got this as dou rho by dou t plus del dot rho v is equal to 0. And here d by dt of this delta m is equal to 0. And here we get, okay, here integral I have to get. Like this. So here d by dt of rate of change of total mass is equal to 0. This is differential equation. So this is the way we get 4 equations. 1, 2, suppose like this is 3 and this is 4, like this. Okay, so if I want to prove this all are similar, okay, so we will take the first equation. Okay, so here, because the volume, I have fixed volume, it is not changing with the time, right? The volume will be same. So this can be taken inside. So I can take this as dou rho by dou t dv. Plus, using divergence theorem, what does divergence theorem says? It converts surface integral to volume integral, right? So whatever is there here, it will become del dot divergence of that is equal to 0. So both becomes volume integrals, which can be combined. So it can be like this. So I have taken the first one, and so this is equal to 0, and I have taken an arbitrary volume. So this must be true for any volume. If it is true for any volume, then the integrand must be 0. So which says that dou rho by dou t plus del dot rho v is equal to 0. So we get the second one like this. Okay, so if I take this, actually the fourth one, d by dt of, yes?
Sir, like in the previous case, like can you say why we took dou by dou inside of the integral? I didn't get it.
Yeah, because it is, I have taken a fixed volume, it will not change with time. So whether it is outside or inside, it doesn't matter.
Okay, sir, got it.
Right? Okay, so d by dt of rho dv equal to 0. And if I differentiate this, so I will get, because rho is 1 and dv is 1, d rho by dt dv plus rho d of dv by dt. And here I divide by dv and multiply dv. So this will become d rho by dt dv plus this is rate of change of volume per unit volume, like this, right? So what is this? Actually volumetric strain. This volumetric strain is nothing but del dot v. So is equal to 0. And I can write this as d rho by dt this is the fourth one. Okay, and so if I expand this, d rho by dt is dou rho by dou t plus v dot del rho, right? Because the substantial derivative is local derivative plus convective derivative plus rho del dot v equal to 0. And if I combine these two, this will become del dot rho v equal to 0. Okay, I can just show you how it is in a better way. If I write in Cartesian, you will understand better, right? And suppose in Cartesian, if I write d rho by dt plus rho del dot v equal to 0, right? So d rho by dt is dou rho by dou t plus u dou rho by dou x. This is convective derivative plus v dou rho by dou y plus w dou rho by dou z plus rho into dou u by dou x plus dou v by dou y. Anything if you don't understand, you ask me, right? Is equal to 0. So I write dou rho by dou t plus u dou rho by dou x and rho dou u by dou x. If I combine, I get dou of rho u by dou x plus this and this I combine, dou of rho v by dou y plus dou of rho w by dou z equal to 0, which is dou rho by dou t plus del dot rho v is equal to 0. This is the third one. Am I clear about this derivation?
Yes, sir.
Right? And okay, another particular thing now I will tell you. Okay, so this is the fourth one I got. This is the third one. If you compare, both are same, right? If you compare these two expressions, in the first expression, every derivative, okay, this derivative, this derivative, this derivative has a coefficient. But if you consider this particular fourth version, I don't have any coefficients for the derivatives. This is one of the main difference you observe, and this type of thing is called as non-conservation form. And this is called as conservation form. In conservation form of equations, there will not be coefficients for derivative terms. Okay, in non-conservative form, there will be coefficients for the derivative terms. In CFD, this conservation form of equations are more important. Later, we will see what is the use of it, right? But this is important. So always Eulerian system comes with conservative form, but many times you can convert because all are equivalent. I am telling, so I can convert them. But if you have in conservative form, either direct or indirect after conversion, that will be the right way of solving for CFD equations. Okay, so this is this. And another thing is, so integral d by dt rho dv. This is the third one actually. Yeah, in the previous one actually, this is not third, this is second. So here also I can write this as and if I write this as okay, just I will do like this. Yeah. Okay, similar to the previous one, I can do that. D of dv equal to 0. And again, this can be written as del dot u. Like this I can do. Okay, just you can go through this. Is everything is there in Anderson. And one more thing, I think you have learnt about what is called as Reynolds transport theorem. Anybody remember what is Reynolds transport theorem?
Sir, sir, in the previous case, like you told we got the sum as 0. You said that integrand is 0, right?
Yeah.
So, like in which cases the integrand won't be 0, sir?
No, if I take a particular volume for which I know the limits, right? The only for that particular volume it is 0. Okay, that integral. But if it is, I say it is true for any volume, any arbitrary volume. So the whatever be it is independent of the limits. Is it clear?
Okay. Okay, sir. Okay, sir. Got it.
Okay, like that. Otherwise, there is a particular volume for which I have a particular limits. Only for that only that integral is 0. Okay. So anybody knows about Reynolds transport theorem? It is actually relates rate of change of property for a closed system and control volume. Okay. Okay. If I take something like this, the rate of change of any extensive property, and is any extensive property is equal, if eta, I will say the corresponding intensive property. Okay, so rate of change of any particular property of a system is equal to the rate of change of property within the system plus the rate of efflux, we call it as. Okay, eta rho BD. Okay, so this is whatever amount of that particular property is leaving, and this is the rate of change of property within the control volume. The total is equal to the rate of change of property within the system. Is it clear? This is what is called as Reynolds transport theorem. Rate of change of any extensive property of the system, that is n is equal to m eta. Okay, this is mass. And so here, dou by dou t of eta rho dV, eta into this mass, right, for a small volume, and it is integrated over the whole volume. So this is rate of change of mass within the control volume. And V dot d, I told this is the property that is leaving. Okay, so mass into this property. So this is the property, net property that is leaving the system. So the total is equal to the rate of change of property within the closed system. This is for closed system, and this is for open system or control volume. This is what is called as Reynolds transport theorem. Okay, what is the use of this is, usually we define conservation form of equations for closed systems. So what we say is the rate of change of mass is equal to 0. This is what is called as continuity. The total rate of change of mass of a closed system is equal to 0. And similarly, the rate of change of momentum is equal to the external force. This is Newton's second law. Because all are rate equations actually. And this is for linear cases. And if it is a rotational thing, then it will be rate of change of angular momentum. It is something like is equal to
Torque. External torque.
okay. So it is for angular momentum. This is linear momentum. And similarly, energy equation, how can I write? dE by dt, or I will say me, or d of e, total. This is total energy, this is specific energy. Okay, is equal to q dot minus w dot. Just not thermodynamics. And okay, this is the way these are actually defined for closed systems like this. And so here, for this, we use what is called as the Reynolds transport theorem. Okay, so if mass is these are extensive. This is extensive property. This is extensive property. This is extensive property. This is extensive. Here n is equal to m, so eta equal to 1. Here n equal to mass into velocity, and so eta equal to velocity. And here n equal to m r cross v, so eta equal to r cross v. And here n equal to total energy, and eta equal to specific energy, like this. So I can use that particular Reynolds transport theorem here. So dm by dt equal to 0. So dm by dt is nothing but so eta rho dv plus is equal to 0. Okay, this is the way. Dm by dt equal to 0. If it is used Reynolds transport theorem, I will get that equation what I got for Eulerian system, right? The first equation. So this I have converted to del dot rho v dv, and then I added these two, and I got dou rho by dou t plus del dot rho v is equal to 0. This is the way I got. Is it clear what I am telling?
Yes, sir.
Okay. So this is the equation we are interested in, Eulerian differential form of equation. This is the equation we use. So this equation is used if you use finite volume method. There are two types when you finite volume method. Either it uses directly integral form of equation, or integrate differential form of equation. Okay, so that is the way we do. And anyhow, this is the equation we deal with. So dou rho by dou t plus del dot rho v equal to 0. Now for simple cases, if you see, if it is steady flow, what is the equation?
Divergence of rho v equal to divergence of v equal to
Del dot rho v equal to 0. Okay. So if it is incompressible flow,
Del dot v is equal to 0.
so because rho is constant, if it can be taken out, and dou rho by dou t is 0, and here rho can be taken out, so del dot v equal to 0. Okay, and which is nothing but dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. If I take a 2D case, 2D incompressible, dou u by dou x plus dou v by dou y equal to 0. Okay, some more important things we will see, which we already have studied. So whenever a mathematician sees this type of equation, he remembers. Okay, suppose because you know that dou square of some property by dou x dou y minus dou square of property dou x dou y equal to 0. Okay, so if I put some psi here like this, and because dou u by dou x, if I want some dou square psi by dou x dou y from here, so I define u equal to dou psi by dou y. So that dou u by dou x becomes dou square psi by dou x dou y. Am I right? Similarly, if v is defined as minus dou psi by dou x, dou v by dou y becomes this. So I can have a scalar defined in this way such that they satisfy the continuity equation. Okay, so a new a scalar psi stream function is defined. Why it is called stream function? Okay, so I will see this property, a contour of this property. If d psi equal to 0, that is the equation of the psi. Okay, so d psi is equal to, how can I, because psi is a function of x and y, dou psi by dou x dx plus dou psi by dou y dy. If I want an equation along which psi equal to 0, right? So this is equal to 0. And dou psi by dou x is minus v dx plus dou psi by dou y is dy, u dy equal to 0. This is the equation of a line along which psi equal to constant. Okay, because I know that later I will define psi is streamline. So this is equation of streamline. And what is the slope of the streamline?
Velocity.
Yeah, so here if you see, because minus v dx equal to u dy, so u dy equal to v dx, and dy by dx on which psi equal to constant is equal to v by u. So if I have velocity capital V like this, and the vertical component is v, small v, and horizontal component is u, and so the slope of velocity is equal to v by u, and streamline velocity slope also v by u. That's why the velocity is tangential to the streamline. Okay, slope of velocity is equal to slope of psi. Therefore, velocity is tangential to psi line. Therefore, psi is called stream function, or constant psi line is called streamline. Okay, so that is this. And in the same way, if you come to irrotational flow, so what is the condition for irrotational flow?
Curl of velocity vector is
Vorticity equal to 0, or curl of velocity is equal to 0. So if I take a two-dimensional 2D irrotational flow, that is along the xy plane, if it is rotation is 0, the z component of this is 0. And omega z, we have seen that dou v by dou x minus dou u by dou y equal to 0. Again, in the same fashion, whenever a mathematician sees like this, here also there must be a similar to stream function, something must be available, because dou square by dou x dou y minus dou square by dou x dou y, again if it is equal to 0, right? So I can put some scalar here so that I will get this. So v equal to, I will write it as dou phi by dou y, so that dou v by dou x becomes dou square phi by dou x dou y. Similarly, u is equal to dou phi by dou x, so that dou u by dou y again becomes dou square x by dou square by dou x dou y. And so this satisfies this equation. Okay, here the gradient of phi gives the velocity, gradient of phi in x direction gives x velocity, in y direction gives y velocity. So this is like velocity, the potential, right? Electricity potential. The current depends on the potential difference. So here also the depends on how phi is changing in x direction, u is there. Okay, velocity in that direction. That's why phi is called as velocity potential. Am I clear? The physical significance you have to understand why they are named like that. Velocity potential. Okay, and Again, if you see what is the equation of the potential line, so d phi is equal to phi x dx plus phi by dy. Phi x means dou phi by dou x. Okay, this is phi x, this is phi y. So phi x is u dx, phi y is v dy equal to 0. This is the equation of the potential line. Okay, so if you find out what is the slope of the potential line,
minus u by v.
by v. And now we can see that the dy by dx of psi into dy by dx of phi, streamline and potential line, v by u into minus u by v is equal to -1. That's why what we say,
Perpendicular.
and potential lines are orthogonal to each other. And if you draw the streamlines and potential lines, that network we call it as flow net. Network of those lines is called as the flow net. Okay, so these are some details. And another important thing I will tell you, right? So a streamline like this, it is there. So anywhere the velocity is tangential to this. So what is the normal velocity?
0.
0. Okay, there will be no flow crossing a streamline. Am I right? No flow crosses the streamline because everything goes tangential to that. There is no flow crossing the streamline. So every streamline acts like a wall. Am I clear?
Yes, sir.
Yeah. And if I have another streamline like this, okay, so this is one wall and that is one wall, and the two adjacent walls, two adjacent streamlines acts like
Stream tube.
a stream or a channel. A channel in 2D, it is like a channel, right?
Sir.
So because of this, the advantage I will tell you many times, if you see a streamline pattern, right, for a physical flow, by seeing the streamline pattern, you can understand where the velocities are high, where the velocities are low. Because if this is a channel, whatever flow enters, the same flow leaves here. So if the area is decreasing like this, what happens to velocity? Because the same mass is going like this. Okay, so as area decrease, velocity increase. Am I right? So as area increase, velocity decrease. And this acts like a nozzle. This acts like a diffuser. Am I clear?
Yes, sir.
And remember, I am talking everything with incompressible flow only. This will not be true for compressible flow. If it is in compressible flow, for subsonic it behaves different way, supersonic it behaves different way, that you have studied in nozzles, right? But for fluid mechanics people, this is the way. Area increase, velocity decrease, velocity increase, area decrease, something like that. Okay, so in the same way, by seeing the I'm seeing the velocity pattern. Okay, so suppose I see here. Like this, you can see that these are away from streamlines are away from each other. So here velocities are very low, and here all gets compressed like this. So here velocities are high, and here this is the minimum velocity stagnation point. Am I clear about it?
Yes, sir.
So later we will see from Bernoulli's equation. If velocity increase, pressure decrease. If velocity decrease, pressure increase. So if I see an incompressible flow pattern, by seeing the streamline pattern, I can say where the velocities are high, where the velocities are low, where the pressures are high, where the pressures are low. Everything I can just immediately physical significance I can tell. Am I clear about it? Is it okay?
Yes, sir.
Yeah. So this is what I want to talk about continuity equation, and briefly I will just say momentum equation. So momentum equation. So d of mv by dt is equal to force. So this is the external force, and these forces are classified as, can anybody say, surface
Body force and surface force.
Yeah, very good. Okay, what is the difference?
Surface force acts on the area, body acts on the volume.
Control surface and act on whole control volume. Okay, so that is the difference. What are the surface forces we deal here? Pressure force and
Viscous force.
viscous force. Okay, these are the forces we consider here. And okay, this we call it as inertia force. Okay, and so we will see like this. So I will see how the forces will be. Okay, and so this is dx. And like this if I have, and if this is the, I can consider pressure force. Okay, so this is pressure acting on this way, and the force is the into the area on which it is acting. Okay, P into dy dz. So here this will be acting like this, and what is the pressure here? P plus, because dx distance I am going, dou p by dou x dx into dy dz. Okay, so what is the net pressure force in x direction?
Dou by dou x into dx dy dz.
In positive x direction. So minus dou p by dou x dx dy dz. Am I right? And force per unit volume if I take, so it will be minus dou p by dou x. This is net pressure force acting in the x direction. I'm trying to find out the momentum equation in x direction. So pressure force I got, and then I will try to get the viscous force. Like this. Okay, and so again, if I take the force acting on this, so the force acting will be tau xx. Okay, you know the stress tensor, right? So two suffixes will be there. The first suffix gives on which plane it is working, and the second suffix gives the direction in which it is working. And this is the x plane. I am talking about the x plane. Okay, so tau xx. Again, the area is dy dz. And here, tau xx plus dou tau xx by dou x dx into dy dz. Okay, like this. Again, if you take the net shear force in x direction, if you take, it will take this minus this. So dou tau xx by dou x dx dy dz. Okay, this is on the x plane. What about the y plane? Okay, this is y. So on the y plane in x direction, okay, so y plane is this. So this will be acting like this, and this will be acting like this. This is tau yx on the y plane in x direction. And what will be here? Tau yx, dou tau yx by dou y into dy. And what is the area of the plane? Dx dz. Right? And again, if you see what is the net force in x direction, so it will become dou tau yx by dou y dx dy dz. In the same way, you will get dou tau zx by dou z dx dy dz. And per unit volume, if I take, so this will be net shear force per unit volume in x direction. Like that I will get. Then coming to the body force, so I take body force B as I.
Sir, can you repeat once, like which suffix represent which one in the shear force?
Yeah, just previous. Okay. So this is y plane.
Yes,
Okay.
sir.
So on 0 y plane, it acts in this way. On if you travel dy distance up, so this will be acting there. And always on the 0 plane, it acts in the negative side, and on the other plane, it acts on the positive side. So the difference when you take, so this will become positive, and this is positive one will get. So this minus this. So tau axis goes up, and this goes.
Okay, sir.
Okay. And body force, if I take Ibx, Jby plus Kbz, this is body force per unit mass. Okay. And so the body force in x direction is equal to Bx rho dx dy dz. This is the mass. So if I take body force per unit volume, it will become rho Bx, like this. So finally, if I take this, okay, inertia force d of mv by dt. Okay, so here m is rho dx dy dz v, and inertia force per unit mass is equal to, okay, here it is not like this actually. Sorry, I wrote this is m into dv by dt. Okay, this is mass and this is the acceleration, and in x direction it will become m du by dt, that is max. Okay, max is equal to m du by dt, and m is rho dx dy dz du by dt, and per unit volume, if I take rho du by dt. Okay, so this is the way I get. And so if I balance this, rho du by dt is equal to minus dou p by dou x plus dou tau xx by dou x plus dou tau xy by dou y plus dou tau xz by dou z plus rho bx. This is Navier-Stokes equation in x direction. Okay, tau by x or tau xy are same. Okay, and in a stress tensor, 9 variables will be there, but 6 unknowns will be there. And in the same way, if I write in v direction and z direction, rho dv by dt is equal to minus dou p by dou y Can you tell me what you will get? Dou tau by x by dou x plus dou tau y by dou y plus dou tau yz by dou z plus rho by. Similarly, rho dw by dt is equal to minus dou p by dou z plus dou tau zx by dou x plus dou tau z by dou y plus dou tau zz by dou z plus rho bz. Am I clear about this? Any questions?
No, sir.
Okay. Okay, now the next question, what we deal with in the next class is, now I have the Navier-Stokes equations. I told the primitive variables are P, U, V, W, and temperature and like that. And now if you see, I have so many other unknowns like stresses are there. Okay, so my equations should be, number of equations should be equal to number of unknowns. But now I have tau x, tau xy, all these stress tensor terms have come. And unless I express them in terms of primitive variables, right, I have additional unknowns. So I had the next thing is how to express the stress tensor in terms of velocity gradients. Okay, stresses are to be expressed in terms of strains, and strains already I know that in terms of velocity gradients, and if I can substitute them, then I will not have any new unknowns. So that is my next task. Okay, and if there are no questions, any questions?
Sir, once can you go to the body force slide?
Yeah, sure. Yeah, like this.
Sir, like here, I mean, we are written it as a vector. No, sir, like, I mean, how will we find the bx, by, bz, sir?
No, okay, it can be anything. Later we will see what is the body force, how to calculate and all those things. Okay, if there is a body force per unit mass is this much. Okay, body force can be electric force, magnetic force, gravitational force, anything. All of them together can be.
So like we are generalizing now, and based on the problem we will use it.
And we will see gravitational force only is the main thing, and how to get them we will discuss later.
Okay, sir.
Okay. Okay, that's it. Okay, this I don't know whether I told this story. It's a nice story. A rich man looked through his window and saw a poor man picking something from his dustbin. He said, "Thank God I am not poor." Okay, this is one of the things we have to learn, understanding that we have many things which other people don't have. There are many things which we have, there are many things which we don't have. But always what we see is we cry about the things which we don't have. There are very few only, but there are many things which we have, but we don't notice them. We take them as granted, right? So there are many people who don't have what you have. And so when you understand that, you will understand. It is like some fellow thinks that he didn't have chapel. And he goes to the temple and he sees so many chapel are there and I don't have chapel and so many people are having. And he curses God. Then he sees a person who don't have legs at all. Then only he understands how fortunate he is to have legs. So in that way, he said, "Thank God I am not poor." The poor man looked around and saw a naked man misbehaving on the street, a madman. And he said, "Thank God I am not mad." And the madman looked ahead and saw an ambulance carrying a patient. He said, "Thank God I am not sick." Then the sick person in hospital saw a trolley taking a dead body to the mortuary, and he said, "Thank God I am not dead." Only a dead person cannot thank God. Everybody else has something to thank God always. And why don't you thank God today for all your blessings and for the gifts of life and for another beautiful day? To understand life better, you have to go 3 locations. One is hospital, another is prison, another is cemetery. At the hospital, you will understand that nothing is more beautiful than health. Okay, you don't know that you are healthy and you have to thank God about it. Only when you go to, I tell many times when some people get depressed, I tell you go to the OP of a government hospital and you will see the real suffering in the world. And then you will understand how fortunate you are. And then in the prison, if you see, you will see that freedom is the most precious thing. And you have the freedom. You are taking so many decisions and so many things you are doing in the way you are like you are living, right? And then only you will understand what is the value of freedom. And at the cemetery, you will realize that life is worth nothing. The ground that we walk today will be our roof tomorrow, right? We will be under the earth. We all come with nothing and we will go with nothing. And let us therefore remain humble and be thankful and grateful to God at all times for everything. Thank you. Thank you very much. Thank you for patient hearing. And go through the Anderson second chapter, right? Whatever governing equations we are doing here, right? It is given in great detail with physical explanations and all, and you will understand still better, right? So because just revision, it will be easier for you and you will understand the things retained. Okay, so once you listen, understand, and go through it again, and if you note down, still it is more better. It gets recorded in your mind. Okay, thank you all. I'll stop recording.
Thank you, sir.